thank you for the introduction, and for, I think, a little bit exaggerated, but what you say, but anyway, thank you. And so I was told that most people will be not expert here, but I see that, in fact, most people are expert. But I prepared a lecture which is for non-expert. So I will talk about the simple Lie groups, and I will not assume that you know what they are. I will define them actually. So let's see. So simple Lie groups were classified by Killing and Cartan, late 1800. And they classified by Coxeter graphs with automorphism. Now, here I should say something which I disagree with the usual notation. So I don't like to call the diagram Dynkin diagrams. I think it's wrong. I want to call it Coxeter diagrams because they were introduced by Coxeter, and so I would say the Dynkin diagrams, that name should be preserved for the diagrams of nilpotent elements. That's okay to use the Dynkin name, but for the Lie algebras, I think it should be Coxeter. And in fact, I remember that in the 1970s I was in England and I met Coxeter. And he was visited, and at that time he went. He told me that he gave several lectures in England. And the title was My Graph. Yes, yes. Okay. So and yes. Okay. So and in fact, so these Coxeter graphs, some of them are called simple-laced. You can see them type A, type D, type E. I think no, this doesn't work. You can E7, E8, and now the other graphs which are I like to use the usual notation is some graph with double bonds or triple bonds, and I suggest that we use a different notation. So type Bn should be. But type Cn should be denoted like this, and Bn should be denoted like this. So there should be really simply laced graph with some automorphism. And I think this contains more information than the other notation, and I think is better. But actually. But in this lecture I will focus on simply laced case, so that they are which are on the one on the left. Okay, so now one of the so after these things were introduced by Killing and Cartan, then much later Chevalier defined versions of these simple Lie groups, where complex numbers were replaced by any field. And actually, in this lecture, I will also talk about some more recent development in which the same groups can be defined over something different from a field. It's called a semi-field. So I will define what this means, but one example is strictly positive real numbers. So there's a version of these groups where complex numbers are replaced by strictly positive real numbers, and this will be instead of being groups, will be semi-groups. These things are actually quite interesting. In fact, you will see that you can understand the usual semisimple groups in terms of these new objects, these groups over a semi-field. This is something which I will try to explain today, how you can. In any case, type AN these semigroups were defined a long time ago, Schoenberg and Ganmacher-Krein, 1930s. So one interesting thing is that these two quite independently discovered in two places which are very close to each other. So one of them is so Ganmacher-Krein were in Odessa, which is, everybody heard it, connects to Ukraine war. So they were mathematicians in Odessa, and Schoenberg was in Romania, in Galați, which is very close to Odessa. So these two people discovered these things at the same time in very, very close distance from each other. So now I want to, since I said that I will not assume that you know what's the definition of the simple group attached to a Coxeter graph, I will give a definition. Now this definition is not a standard one. So the standard definition, in fact, there's one definition which Chevalier gave, is that you first construct a Lie algebra. He starts with a vector space with the basis, supposed to be a Lie algebra, then he defines a bracket, and then there are some huge problems with signs. So it's very complicated to say what are. So there's some signs appearing. It's very complicated issue. So I will give a method which completely avoids this complication. So there's no signs at all. So this is something which I found in 1990. Let's see. Okay. So we start with this Coxeter graph, and I is a set of vertices, and then you look at the free Z module basis given indexed by these vertices, and have a bilinear form with values in Z. Oops. No. This one. And is given by two base elements of inner product 1 or -1 or inner product -1 or 0 or 2. And then we also need a linear function from this Z module to integers for each vertex. So it basically some dual basis. And then we can define a set of roots, which are all elements of this free module with inner product E with itself equals 2. And this is a finite set. And it is union of two positive, these are called roots, positive roots and negative roots. So positive roots are defined like this. Okay, and then now we form a vector space, of a complex vector space with a given basis. So one part of a basis are X alpha indexed by the roots. Another part of a basis, they are Ti indexed by these vertices of our diagram. And on this vector space, there will be linear maps, Ei epsilon from M to M, and they act by this formula. So Ei epsilon applied to X alpha is another X alpha, or 0, or is Ti. So according to the conditions here, and Ei epsilon applied to Tj is actually a multiple of X epsilon alpha I, and the coefficient is an absolute value of this inner product. So it's always some positive integer. So in this form, this matrix of this Ei epsilon is entirely consists of positive entries. I think. Okay, so then now we define for each vertex and each complex number, we define some automorphism of M. So you take this EI1 and multiply by a scalar and take exponential of that. That is xi of lambda, and the other one is yi of lambda. Okay, so there are two families of automorphism, and this complex Lie group attached to our graph is a subgroup generated by all these automorphisms. So that's the definition. Now I will also use the upper triangular part of this group. U plus of C is generated only by xi of lambda. And there's also some commutative part, torus part, is generated by some automorphism tau I of lambda, which are defined here. And that's a subgroup of G of C. Okay, so now, so that's the definition. Now I want to give well, there's something called Wald dimension formula. So this is something which appears in Lie theory, and this will be something which I will explain later in terms of this group over semi-field. So that's one. In fact, almost everything I will say today will be some preparation to give a formula for which express Wald dimension formula in some form which makes it obvious that it's integer. So let me give a formula. So no, it's difficult to have. Yeah, I can see this breaks it into two. So I don't know how to do that. This one, maybe this one. So assume I have a function from the vertices of my graph to natural numbers. I goes to lambda I. And then there is something which is called Wald dimension formula, which is it attached to lambda some rational number d lambda, and it's a product over positive roots of something divided by product positive roots of something else, and this is actually. Turns out to be a dimension of some representation of this Lie group. So it's a positive integer. But it's not at all obvious from the formula why this is an integer. That is totally unclear. So for example, if type A2, which means a graph with two vertices joined, d lambda is a product of three factors like this divided by 2. So in this case, you can see that it's an integer because if lambda 1 is if lambda 1 is odd, then the first factor will take care of the 2, and if lambda 2 is odd, the second factor will take care of the 2, and if both are even. Sorry, no, this should be plus 2, I think. This is a plus 2. Yes, yes. So if both are even, then the third factor corrected at this will take care of the 2. So in this case, you can show that it's an integer. Now let's see. In type A3, the formula is like this product, the product of 6 factors, and there's a denominator. And in this case, you can also prove, with a little more effort, you can prove that it's an integer. But if you go to more complicated case, it's not so clear. Any case, this discovered this thing. He proved that this dimension of some irreducible representation of this Lie group. Okay, so now I want to talk about this group of a semi field. So the simplest case is if you take replace complex numbers by r by strictly positive real numbers. Then you take the same definition as before, but this xi of lambda, y of lambda, you assume that lambda is strictly positive. And you also need this torus part. And there's also u plus, this upper triangular part is also defined in the same way. And now in type A2, there's alternative definition of this, so that is in fact the old definition of Schoenberg and Krein and Ganmacher. So the all 3x3 matrices such that every entry is greater than or equal to, well, has determinant 1, and every entry is greater than or equal to 0, and every 2x2 minor is also greater than or equal to 0. And this U plus, they are upper triangular matrices with the same type of properties. So again, each 2x2 minor, each element and each 2x2 minor is greater than or equal to 0. Okay, but now I claim that this G of you can replace positive real numbers by something more general, which is called a semi-field. So a semi-field is a set with two operations, plus and so addition and multiplication. And addition is commutative, associative. Multiplication is actually a commutative group. And there's a distributive law is satisfied. So there are three examples, at least three. So one of them is real numbers with strictly positive real numbers, with usual addition, usual multiplication. Another one which is integers. This is a very interesting example. So the sum of two integers is defined to be the minimum of those integers. And the product of two integers is defined to be the sum of those two integers, the usual sum. The new product is the old sum. And this is actually very important semifield. There's also another semifield. This semifield is one element. This is also interesting because there's no field with one element. So the field doesn't exist with one element, but semifield does exist. I don't know what is the sound, but did I make the sound? No, no. So if you take this set with one element, then you can define sum of 1 plus 1 equal 1, 1 times 1 equal 1. It is satisfied axioms. So now I want to give a definition of this, but in a definition I will only talk about this upper triangular because I don't want to be too technical. It's a similar definition for G of K, but in order to be less technical, I will also only talk about U plus of K. So it turns out that there's a definition of this semi-group. It is very similar to the definition of a Coxeter group. So Coxeter had a notion of Coxeter group attached to this graph, and this will be almost imitating his definition. So this semi-group has generators I to the power A. So I is a vertex of the diagram, and A is an element in a semifield. And then the product IA IB is IA plus B. Then IA JB equals JB IA if the two I and J are not connected in the graph. And there's a more interesting relation if you have I and J which are connected, then you have a formula like this. It looks like a braid group relation. But this relation between this ABC and A prime, B prime, C prime is given by these formulas, and you can these formulas are symmetric. If you replace ABC by A prime, B prime, C prime, you get exactly the same formulas, which is quite nice. So this similar definition of a Coxeter group. And there's a special case when the semi-field has one element. So in that case, you get this three type of relation, and this looks exactly like relation of Coxeter group, except the first relation is different. Because in the Coxeter group, you would say that I1 times I1 is the unit element, and here is not a unit element. So actually, this what you get from this will be not a group, but a semi-group, which has the same. These elements are same indexing set as for Coxeter group, but relations are slightly different. So now I need some notation in this U plus corresponding to the to field semi-field one element. There's a notion of length. So this is a minimal number k, such that U is a product of k generators. And then denote by nu the maximum value of this length. So, and then you can look at all sequence. This I will be all sequences in vertices. Number of terms in a sequence is this number nu, and you want relation I1 to 1, I2 1, I nu 1 should have length nu. So there are finitely many such sequences, and for example in type A2, which has two vertices, then this set I, this script I consists of the two elements, iji and jij. Those are two elements. Okay, now there are some parameterization of this semigroup. So if you take any such sequence in this set script I, we define a map from k nu to this U plus of k by this formula A1, A2, A nu goes to I1, A1, I2, A2, I nu, A nu. And there's a theorem which can be proved is that this map is injective and its image is independent of the choice of this sequence I1, I nu. And this image is also itself a semigroup, sub-semigroup, but it's not without unit in general, and is denoted by U plus strictly positive of k. And this set U plus strictly positive k is in bijection with k nu in many different ways. So for each of these fi gives a bijection. So we have a set, a semigroup which is parameterized in many different ways by k nu. Okay, now the next thing is that you can assume now that k is integers. I said that integers form a semi-field in an interesting way, and so you can specialize the discussion to the integers. And then you can take but then take sequences of integers which are all positive. So that will be So I can take the image of n to the nu under any of the maps that I had before, and I claim that the image of that is also independent of I, and it's also a semigroup. So this is denoted by U plus strictly positive n. And so this is a semigroup in bijection with natural number to the nu in many different ways. For example, in type A2, which I mentioned before, this corresponds to all products I, A, J, B, I, C, with A, B, C natural numbers. And this can be also written as product of J to the A prime, IB prime, J to C prime, or again natural numbers, and their relation between those two parametrizations is like this. This one equals this product. You remember that in this semi-field, this minimum of two numbers plays the role of a sum, and this thing actually should be interpreted as a product of B times C divided by the sum of A plus C. That's what you do in this semi-field, and actually you have to notice that if A, B, C are positive, so natural numbers, then this is automatically positive also, because for example, because if you take C and you subtract minimum of A and C, you get something positive or zero, because you subtract something which is not at most C. So if these are positive, this will be also positive, and all the others are positive. So that's how you prove that this. In this case, that's how you prove that the two description of these sets agree with each other. So this makes sense over natural numbers. Okay, so now. Okay, so now for each vertex of our graph, there is a well-defined function zi from this semigroup, integer semigroup, which is given by the following formula: that you take some element of this semigroup, which is product I1, I2, I nu. But you insist that it start with I1 equals I is the one the fixed is the one given to you, and then you look at the exponent of the first of I1, and that is the value of Zi, and then there's a lemma which says that this is independent of the expression you use, independent of any choice. And this follows from theorem of Matsumoto, which says that you can that any two which says that any two such expressions which start with the same letter can be transformed into each other by some elementary moves. Anyway, so that theorem tells you that this is well defined. Okay, so now I will go to I will try to explain how this wide dimension formula is can interpreted in terms of this semi-field, semi-group. So assume that you have a lambda which is a function from the vertices of our diagram to natural numbers, and then you can take we have defined. So we have defined this thing without exponent lambda that we have defined, but now we define the subset corresponding to lambda. So you take all elements in this semi-group such that if you apply zi to it, then you get something which is at most lambda I. So that should be true for every I. And then this theorem which says that the number of elements in this set is exactly the same as Wild dimension formula. So this gives some explanation which is why the d lambda is an integer. And by the way, this is something which I knew a long time ago, but for a long time I didn't know. I was missing. I didn't know why this right hand side is finite. This was not obvious to me. And this is something I recently found a way. It's not difficult to prove that it is. So there is some a priori argument that this thing is finite. In fact, it is. It is. So if lambda I is if each lambda I is less than some number n, then number of elements in the set can be bounded by something like 1 plus n times 1 plus 2n plus 1 plus 4n plus 1 plus 8n, something like some product like that. So there's a so this is something which so I say that in this lecture almost everything I say is very old, but in this particular thing it's something which I found more recently. But okay, so maybe I'll give an example. So in so suppose you are in type A2 and you have two simple there are two the graph has two elements I and j, and then this set un positive in lambda can be identified with the subset of n cross n cross n, 3 copies of n, and the conditions is that you see this one condition is that this A should be less than lambda I, but there's another condition which says that after you write it in the second corresponding to the other reduced expression, then the coefficient of that first coefficient of that should be also less than lambda j, and that coefficient is basically b plus c minus minimum of ac. So actually this number can be decomposed into two parts, depending whether A is less than C or bigger than C. And if A is less than C, then the condition is B plus C. Here, B plus C minus A. And if A is bigger than C, then then just be less than lambda j. And actually, this you can count. It's very easy to compute how many such triples you have in each case, and you find that it is this one plus this one, and the two things together will give you exactly d lambda. Mm-hmm. Okay, so now I give you another application. Well, here you don't use the semifield itself, but you use some ideas which came from this theory of a semifield, which is so the problem is to describe the coordinate ring of this Lie group U of C. So this is something which I did with Fomin. I conjectured it and we proved it in a joint paper. So this is based on a joint work with Fomin, 2020. So anyway, so what I want to say is that this U upper triangular part of the Lie group is supposed to be an algebraic variety. So it means that there's a notion. So it's supposed to have a coordinate ring. So there has to be a notion of regular function, and those form some algebra. And if you want to understand this group, you would like to know explicitly what are these algebra of regular functions on U. And by the way, there's a similar result to G itself, but again, in order to simplify for this lecture, I will only talk about this U instead of G. So now remember we have this notion. You consider a sequence I1, I2, I nu. So this notion was defined in terms of this U plus over semifield one element. That was defined, and now we define a map from C to the nu to this group U by A1, A2, A nu goes to xi1, A1, xi2, A2, xi nu, A nu. So this is a product in U plus of C. So which means that there are many maps from C nu into U. So the family of finitely many such maps that we consider. So now we define O of U to be all functions from U to complex numbers, such that when you compose H with any of this Fi, then the resulting function is from C to the nu to C, and that is supposed to be a polynomial function. So this is not an obvious result. So I claim that that's a description of the coordinate ring of U, and it is based on these ideas of this U plus over semifield. So okay, so that's a theorem. So OU is a coordinate ring of a structure of algebraic variety, which makes U an algebraic group, and a similar result holds over for G of C. Okay, now. Okay, so actually I finished all my slides, what I prepared, but I can still say, maybe I can still say something. So that's what I prepared. Yeah, usually what happens, this goes faster than you expect. If you don't write on a blackboard, it is faster. Okay, so so maybe I can also say something another interpretation of this u plus, where is it, of u. This u plus of n, u plus positive of n. So that's a kind of historical thing. So this set appeared actually before I was interested in total positive theory, namely when I studied canonical basis of quantum of u upper triangular part of a quantum group. So in that case, again, for let's say so simplest case, so this upper triangular part of a quantum group had a basis, and it was in bijection with. So there was also Poincare-Berkowitz basis. But there are many such Poincare-Berkowitz bases, and it's basically one for each I, like this, each of these I, and then this Poincare-Berkowitz basis is indexed by sequence of natural numbers A1, A2, A nu. So that is also an example where you have some set parameterized in many different ways by sequences of natural numbers. And in fact, in that case, I found that the transition between two of those parameterizations is exactly what I described here. But at that time I didn't know a definition of this semigroup. But in fact, this semigroup appeared for the first time in this context. Which means that this canonical basis, basically, it is a semigroup attached to these natural numbers. Now I should say that in yeah, so here I always assume group simply simply laced, but if a group is not simply laced, so this semigroup is also defined in the non-simply laced case. And then canonical base is also defined in non-simply laced case. And basically you have to use this simply laced case with an automorphism, and you take some invariant, some orbits of the automorphism on this semigroup for a simply laced group. So in some sense, the theory of non-simply laced groups can be reduced to simply laced group. In fact, I was also thinking that maybe in a lecture we have heard yesterday, it's possible that you can also treat that, which was about this affine Cn. I think it's possible that you can also study that by reduction to a simply laced group. That's what I would think. Um, Actually, in this I also say that in the I think in the beginning of this in the first page of this presentation, we had all these Coxeter diagrams. And actually, they all have a affine analog. So there is a affine type A, affine type D, etc. And then there's a larger picture which are so-called affine Cartan matrices. And in fact, it is also the case that all of those can be described in terms of simply laced affine diagrams with some automorphism. This is something which I did in my book, and I think it should be. I believe that can be used for various purposes to prove things about non-simple laced groups. Okay, maybe I stop here. So.